Welcome to EE252 Electronic Devices and Circuits. Today we are going to talk about bandwidth of a BJT amplifier. Actually, this is more general than just for a BJT amplifier. This applies to any amplifier or any device. But since this is relevant to our study, we are going to look at it today. Okay. So far, the effect of coupling capacitors was neglected in our circuit. So when we wanted to input a signal to a BJT amplifier circuit, what we did was to couple it through a capacitor to avoid any upsetting of the bias. So you initially have a bias, and then to couple an AC signal without having to worry about its DC component, we send it through a coupling capacitor. Now, what is the effect of these coupling capacitors? We did not actually look at it so far. We said it acts like a short circuit for the signal in frequency, but it's open circuit for DC currents, DC voltages. So, but the issue is now, since we are looking at low frequency, small signal circuits, okay, at low frequency. So the frequency of interest, the range of frequencies that we are interested are the audio frequencies. That's basically 20 to 20 kilohertz mainly. So at lower end of these frequencies, the capacitors, the impedance of a capacitor is proportional to 1 over frequency, right? So XC, the impedance of capacitor, is equal to 1 over j omega c, right? So therefore, as the frequency goes down, impedance increases. So therefore, at lower frequencies like 100 or lower than that, maybe 20, it may have a very high impedance, which may be actually comparable to the components that we have. So in which case we can actually have a significant attenuation due to the voltage drop across these coupling capacitors. This is what we are going to look at, and the effect is going to be, when you have a capacitor, it basically behaves like a high pass filter, and the important question is, what is the cutoff frequency, or more importantly, the lower cutoff frequency of the high pass filter when you use a coupling capacitor. This is what we are going to look at today. So let's look at a voltage amplifier model. So for a BJT circuit, okay, so let's do that. Let me draw the equivalent circuit. The BJT, not just BJT, the amplifier circuit can be represented as a voltage amplifier, where you have the input impedance, the voltage gain AV times VI, and the output impedance R out. Okay, so this is basically my amplifier. This is connected to a load. Let me call it ZL, the load impedance, and this is connected to a signal source VI through a capacitor. Okay, this may or may not have an internal impedance which is significant enough, but let's assume there is the internal impedance of the source is small. Okay, so this is my model, and this is my amplifier circuit. Okay, so this is my voltage amplifier model. Okay, this is my V in, this is my V out, and I have AV times V in as my voltage source. This is R out, this is R in. Okay, so let me write an expression for V in. Let me call this V in terms, let me call this one Vs, the source. Okay, so V in is equal to, so you can look at the capacitance as a impedance. So impedance of this is XC, which is equal to 1 over j omega c, where omega cc, omega is the radian per second frequency, is the frequency in radians per second, right? So what I have is a voltage divider. The voltage input is equal to R in divided by R in plus XC, like that. So times Vs, right? So I can write this as R in divided by R in plus 1 over j omega c, 1 over j omega cc, coupling capacitor, times Vs. This is equal to R in plus. So if I divide top and bottom by R in, I will end up with 1 over 1 plus 1 over j omega cc times R in, okay, times V in Vs, which is equal to 1 over 1 minus 1 over j omega cc R in times j. There's no j here, so I can take the j up, so I can multiply top and bottom of this by j. So you multiply j here and j here, j squared is minus 1, so that is why you have minus 1 here, okay. If I want the j on the top, so what I can do is I can multiply this by 1 plus j 1 over omega cc R in top and bottom. So you will have 1 minus j 1 over omega cc R in times 1 plus j 1 over omega cc R in. So this is like 1 minus x times 1 plus x. So this is 1 minus x squared. So you have 1 plus j 1 over omega cc R in divided by 1 minus this whole term squared. So j squared times this squared. So j squared is minus 1. So this becomes 1 plus 1 over omega squared cc squared R in squared, okay, times Vs. Now in this expression, what happens when omega is equal to 1 over R in cc? At this particular case, omega is equals to this, so that 1 over this, so that means this whole term becomes 1. So what we will end up with is V in is equal to 1 plus j divided by, again here what you have is 1 divided by 2. So 1 plus 1 is 2. Okay, so this is what you have times Vs. This is equal to 1 over square root 2 e to the j pi by 4 times Vi in terms of the phase notation of the in magnitude and phase. So this is my phase. Phase is that. Okay. So if you take the absolute value of this, the magnitude of this, V in magnitude, what I will get is 1 over square root 2 times Vs, because absolute value of this component is equal to 1. Okay, so therefore this is what I have. Now you see that the absolute value of the input voltage you get is 1 over square root 2 of the input voltage. Now you know the power, when it comes to the power, okay, power is proportional to voltage squared. So therefore the total power that is going into the circuit, power in, is actually proportional to half of this, which square of this is like 2 V squared, right? So this is, if the input power is proportional to V squared, so this is half the input power, source power. Okay, so therefore I only get half the power into my circuit. So this particular frequency, therefore we call the cutoff frequency, or the, in this case, so this is called the cutoff frequency. This is called the cutoff frequency, because this is from the lower side, we actually call this lower cutoff frequency, or omega L. Here we call this the omega L of the filter, where omega L, from this expression, omega L is equal to 1 over R in times Cc. Okay, this is actually 2 pi times lower cutoff in hertz. FL is in hertz, right? whereas omega L is in radians per second. Okay, so what this looks like is, let me draw it here. This is my frequency, this is my V in, okay, divided by Vs. So when omega is rather high, what you have is almost all the components actually go into the, so it's, if you look at this here, when omega is high, then what you will have is, because this is very high, this term almost equal to 0. Similarly, this is almost equal to 0, and therefore what you have is V in is equal to Vs. So therefore what I have is something like this. This is 1. But at lower frequencies, this starts to roll off. Okay, and at which point you have half the power. In other words, 1 over square root 2 is at 0.707, that is square root 2 of the voltage. You have this frequency which we call omega L, lower cutoff frequency. In fact, if you increase the frequency further and further, what will happen is the parasitic capacitance or the leakage capacitance between each of the terminals of the transistor will also be significant. The impedance due to that will be significant, they will be small enough so that there will be leakage current, and actually the current will not, some current will actually not flow into the transistor itself, so therefore will not get the required gain. So at some point, if you have very high frequency, what will happen is this will roll off from the other side also. The frequency at which you get that we call the upper cutoff frequency. Okay, upper cutoff frequency, WU. This is called upper cutoff frequency. This is due to parasitic capacitance due to base emitter, base collector, and collector emitter terminals. Okay, so let me give you that also as a note. This parasitic capacitance actually is not any particular capacitor that we have inserted, but they are inherent capacitances that are there because there are two terminals, and between any two terminals you can have a small capacitance, unintended, unwanted capacitance. So those unintended capacitance values, very small values like picofarads, or maybe tens of picofarads, or maybe hundreds of picofarads, but still at high frequencies these become significant. The impedance becomes important for us. Normally at lower frequencies they have giga-ohms or hundreds of mega-ohms or something, but very high frequencies they can come into kilo-ohms or tens or hundreds of kilo-ohms. If they are similar to the parameter values that we have in our circuit, then not all the current will flow through my components, rather some currents will flow through these parasitic capacitance and lower my gains. So therefore we need to think about it, but this is out of scope for this course, so therefore we are not going to talk about it any further. But one other thing that we need to remember is that in addition to the coupling capacitors, we may also have some other capacitors, like for example emitter bypass capacitor. So the effect of that needs to be taken into consideration when we actually calculate the bandwidths, because sometimes these coupling capacitors may not have the effect that is expected out of it. So therefore we need to carefully consider all the cutoff frequencies due to each of these coupling capacitors and other capacitors, and the actual lower cutoff frequency for the amplifier depends on the highest of all these values. Okay, so that also let me write down. Okay, this is where we are going to stop today. So this is about the bandwidth of an amplifier. Thank you.